Yeah, can you graph the prime horizontal line?
Oh, it's y equals 0.
Oh.
So if you have a horizontal line for your original function, y equals f of x, which is this horizontal line. The slope everywhere is 0, so when you come over here and graph the derivative, because everywhere the slope is 0, the derivative is only going to have 0 y values. So this is f prime. So that one's kind of strange, I suppose, because they're both horizontal lines, but this one's a 0. What else?
Can you give us more examples like those? Because I'm having, I understand it when we're going over them in class, but like on the quiz and on the homework, they're just, I don't know, they're not.
Well, then probably me going over them in class again isn't going to make you understand, but I can if you want. Like, I can do examples all day, it doesn't bother me. But if it didn't work the first time, that's the definition of crazy, right? You try the same thing over and over and expect different results. So, suppose I gave you this guy. Y equals f of x. And specifically, so the kind of problem we're talking about here is I give you a function, I want you to graph the derivative. Okay? So what's really important when you're graphing the derivative of a function is where it has a horizontal tangent line, right? So that, another way of saying that is where the function turns around. Okay, so the very sort of important x values here, say this is at -1, and say this is at So if I give you this function, right, with this maximum at x equals -1 and this minimum at x equals 3, you should be able to sketch a decent graph of the derivative. Over here. When you're analyzing the derivative, you first focus on where you have your horizontal tangent lines. M equals 0 here, and m equals 0 here. So the slope is 0 at these two x values, which means the actual y value is 0 on the derivative. So this 0 slope turns into this y value of 0 over here. Both of those 0 slopes will give you y values of 0 on the derivative. Other than that, focus on where the slope's positive and where it's negative. So over here, for example, m is positive, while over here, m is negative, and over here, m is positive. So your function has to be positive, meaning that the y value, or your derivative has to be positive, meaning the y value has to be above the x-axis. Right? This part of the axis is where y is positive. And this part of the axis is where y is negative. Since the slope is positive over here, that translates to y positive on the derivative. So you have y positive before -1, y negative after, and then y becomes positive again after 3. Right? Because it goes positive, negative, positive on the slope, it goes above the x-axis, below the x-axis, above the x-axis on the derivative. Yeah.
On the homework.
Sure.
2.2, number 19, which is y equals pi over 2 sine.
Pi over 2 sine theta.
Theta, thank you.
Minus cos theta. And it probably wants you, okay, so this is number 19 from 2.2. Use the rules of differentiation to find the derivative of the function. Okay, okay. So, remember your differentiation rules? Maybe kind of.
Pull out the pi over 2, cosine theta, sine theta.
Yeah, so there's a couple. So just as a refresher, remember we said that if you take the derivative, this isn't super useful in this problem, but just as review. If you take the derivative of x to the n, what do you get? Nx to the n minus 1. Right? This is called the power rule. Yeah. That's one thing we did last time. Then we talked about the derivatives of sine and cosine. So if you take the derivative of sine, what do you get? Regular cosine. However, if you take the derivative of cosine, you get negative sine. So these are your trig derivatives right now. Now, in this case, we had a couple other rules like constant multiples can be pulled out of the derivative. So what I'm going to do here is, because I have a constant multiple, I'm going to take the derivative of sine and then multiply the answer by pi over 2. Okay, so whenever you have a constant out in front, you can ignore it at first when you're doing your derivative. So I'm going to do the derivative of sine, which is equal to what? Cosine. But then because there's a constant multiple, I'm going to bring that down. Now I have to do here the derivative of cosine. So the derivative of cosine is just negative sine. But there was already a negative. So it looks like this. So altogether you'll get y prime equals pi over 2 cos theta plus sine. So the constant multiple, the multiple out front just follows all the way down. And then you do the derivative of the function separately. That's all there was to it. You had to know these. You had to know that the constant multiple follows.
What about 49?
49. Okay, root x minus, it says find the derivative, okay. Root x minus 6 cubed root of x. They call it y or they call it f? They probably call it f, just on this one. They call it f, okay. So we have this function, they want us to find the derivative. df dx, the derivative. Now, before I can actually do the derivative of this function, I'd really like to make it look like something that I can handle with one of my rules. So you want to always try to rewrite radicals as powers before you do any calculus. Okay, so before I actually do this derivative, let me rewrite these radicals as powers. Root x is what power? X to the 1/2. Minus 6, and then cube root is x to the 1/3. Square root 1/2, cube root 1/3. Fourth root 1/4, fifth root 1/5, etc. Now I can do my derivative because both of these look like x to the n. So I'll do df dx equals, the rule tells me I have to bring the 1/2 down and then subtract 1 from the power, so I have to calculate 1/2 minus 1. That's not too bad. So it'll be 1/2 x to the negative 1/2. Same thing with the 1/3. It's got to come in front. Because this is a constant multiple, I'm going to ignore it at first and just do the derivative of the x to the 1/3. When the 1/3 comes down, it's going to multiply to 6. And then you subtract 1 from the power. So this will be minus 6, but then you'll multiply by the original power. And then you'll have x to the negative 2. So if we clean this up a little bit, x to the negative 1/2 can be brought down as a square root. Down because it's a negative exponent, square root because it's 1/2 power. 6 times 1/3 is 2. And then x to the negative 2/3 can be brought down as well. It'll be cube root of x squared. Put it here. So this is one way to write the derivative. I don't want you to go overboard simplifying, because you're bound to mess up somewhere. I just want you to get your derivative right. However, Larson or in the back of the book, you're probably going to see some crazy simplifications. So if you can't get what he gets, let me know. I'll probably not be able to get what he gets either. So any questions about this one? You see where I'm going here? Okay, okay. What else? Too easy? Yeah? No? Yeah? Pretty easy?
Don't wait, but please, just 1 second, I'm so sorry. Ah, please.
All right, so I was going to do some review anyway. I have some review questions to work through with you guys, and then we'll start 2.3. If you didn't give me your quiz yet, you can bring it up here for me now. Or whatever, get it to me sometime. And then I will bring you another take-home quiz next time on Wednesday over 2.2 and probably 2.3 since it's take-home. But for now, let's do a little more. Find each derivative. Or find the derivative of each function. We'll start with an easy one. F of x equals 13x to the 5th. What's f prime? What's the derivative? $65x to the 4th, right? The 5 comes down, gets multiplied by the 13, you subtract 1 from the power. 5 times 13 is 65, so f prime is 65x to the 4th. So if you have a function of this form, x to the n, even if there's a number in front, you can apply the power rule. What changes if I give you something like this? 13 plus x to the 5th. Is that the same idea?
No.
Totally different. What's the derivative here? Because this is connected by addition, you take the derivative separately. So you have to take the derivative of 13, which is a constant, so you get 0. Derivative of a constant is 0. Then you take the derivative of x to the 5th, which is 5x to the 4th. So when it's connected by addition, you take the derivative separately, which gets your constants to go to 0. So g prime here would be 5x. Okay? If I give you y equals the 4th root of x squared plus 1 over x squared. Well, let's do x. How do we do the derivative here?
Rewrite it
3/4
first.
x.
Right, so do your algebra first. Rewrite it as an exponent. So this will become x to the
3/4.
3/4. The root is always on the bottom and the exponent's on the top. Plus, I'm going to write this guy again as what? X to the -2. Now you have the perfect form that you need to use your power rule. So the 3/4 comes down, and you subtract 1 from the power. 3/4 minus 1 is -1/4. What about this guy? Minus 2, x to the -3. I particularly like negative exponents, so I bring this guy down. 3 over 4, 4th root of x, right? 1/4 is the 4th root of x, but it's in the bottom now. Minus 2 over x cubed. There's one. So what about something like this? Square root of x times x plus 5. Oops, let's call this g. How do we do this derivative? What do you got to do first? Do your algebra, right? Multiply it out. Algebra. Rewrite. An idea of this. So you can rewrite the root x as x to the 1/2 first, or you can do it after you multiply, or you can do it in the middle. So in my head, I'm thinking this is x to the 1/2, this is x to the 1, so what happens when I multiply? X to the 3/2. This is x to the 1/2, this is 5, so plus 5, x to the 1/2. That's my original function. Now I need to work in my derivative.
3 over 2x to the half.
There you go.
2.5x to the negative.
So break down your 3/2, then subtract 1 from the power, so it'll be x to the 1/2. Bring down your 1/2, which will get multiplied by the 5. So 5/2 works. But then you got to subtract 1 from the power, so x to the negative. Roots back in if you want. This guy's going to be a root in the bottom because it's a negative. Excellent. Okay. Maybe one more. Something hard. Questions about any of these? No? What if I asked, instead of just find the derivative, what if I said for g of x, find the slope of g at x equals 1? What would you have to do instead? Right, so finding the derivative, you'll do your power rule or whatever, but if it wants the slope at a specific x value, that's still the derivative, but now you have to plug in this x value. So in this particular case, if I change the example a little bit and made it like this, you would have to take the derivative and plug in x equals 1. So this vertical bar, if you haven't seen this before, this is an evaluation bar. It means plug in whatever you see underneath it. So the derivative with x equals 1 plugged in would be 3/2 times root 1 plus 5/2 with a root 1 on the bottom, right? You just plug in 1 here and here. Yeah, so 3/2 plus 5/2 is 8/2. So slope at a specific point means you got to do one more step. You got to plug in your x value. And then what if, just because this is where my brain goes, it said find the equation of the tangent line.
Oh, we need a point.
To G. x equals 1. So I asked you for the derivative in this part, then I asked you for the slope here at x equals 1. Now I want the equation of the tangent line at x equals 1.
Y equals.
Yeah, you need a point, right? For the equation of a line, you need a slope and a point. We have a slope, right? This will be my slope of the tangent line. Now I just need a point. So I have my x value on my point. I just need the y value. How can I find the y value? Plug 1 into the original g function. So first, to finish off my point, to find the y value of my point, I'm going to have to calculate regular g of 1, right? The original g function of 1, which will be root 1 times 1 plus 5, root 1 times 6. So this is my y value. So now I have a slope and a point. Once you have a slope and a point, the equation of a line just comes from a formula. To finish this problem off, I would have to do y minus y1 equals m times x minus x1. That's one way to get the equation of y. I would plug in 6 for y1 because that was my y value. I plug in 4 for m because that was my slope. I got that from the derivative. And then I plug in 1 for x1 because that was my answer. Make it look pretty. Okie dokie. Kind of went off on a tangent there. No pun intended. Stuff is gold, guys. Alright. Questions about that last example? Alright, one more. So again, back to finding the derivative, right? What we were originally doing. So find the derivative of the function. Pretty messy one here. 5x sine x minus 8x cos x plus root x over x. What do you think? How do we do this derivative?
Separate.
Yeah,
Bring the x up.
yeah, right now it's kind of way too complicated for us to even deal with. We do not know how to find derivatives of quotients or products, right? That's what we're doing today. But we can do some algebra and simplify this first. Right? So one way to do the algebra here is to split this into 3 different terms. The x division goes in here, goes in here, and goes in here. So there's a distribution for division just like for multiplication. So this will become 5x sine x over x minus 8x cos x over x plus root x over x. The division by x goes in each term. And each of these should simplify. X and x, x and x. X and root x is going to leave you with what?
1 in the root x over.
1 over root x.
Yeah, 1 over root x. Or 5 sine x minus 8 cos x plus x to the negative 1/2. Right, this guy was x to the 1/2. This guy is x to the 1. If you divide, you'll end up subtracting the exponents, which gives you negative 1/2. And then you can apply the rule we learned. Derivative of sine is cosine. So I keep writing sine. So derivative of sine is cosine is 5 files long, so it's a constant multiple. The derivative of cosine is negative sine. And then the derivative of x to the negative 1/2 is negative 1/2 x to the negative 3/2. You got to subtract 1 from the power. And you do negative 1/2 minus 1. Clean it up a little bit, not too much. 5 cos x plus 8 sine x. Probably put this in the denominator. Square root of x. What do you think? Good? We're prepared? We know the power rule, we know the derivatives of sine and cosine, we know how to do all our algebra? The algebra is going to be the hard part. We'll see how it goes. I left off last time too. I told you I was doing a velocity example. I wanted to do one more of those. And then we'll jump into 2.3. One more. So a ball is thrown downward from the top of a 220-foot building. With a velocity of negative 22 feet per second. So in this situation, there's kind of a general formula that will allow you, when you throw an object up or down, there's a general physics formula that will allow you to find the position function, right? How high the ball is or how high the object is off the ground. This is the formula. S of t is equal to, it depends on whether you're using feet or meters, but if you're using feet, you do negative 16 t squared plus the initial velocity t plus the initial position. I won't make you memorize it. If I ever want you to use it, I'll certainly give it to you. So the acceleration is actually in this factor here. This is the acceleration divided by 2. The acceleration due to gravity in feet, in the units of feet, is negative 32 feet per second squared. So this is the sort of equation you can use, the kinematics equation from physics you can use to sort of model the position of this. But more likely what I'll do is give you this, and then I'll actually plug in everything for you. Right, I'll tell you, in this particular instance, the position of the ball is given by negative 16t squared minus 22t plus 220. Because it was initially 220 feet high, we put the 220 here. And because we threw it down at 22 feet per second, we put the negative 22 here. So this comes from this physics formula. For the most part, ignore this and focus on this, since I'll probably give it to you. So all the questions from here on have to do with this position function of the ball, which tells you S is how high the ball is off the ground at any time t. find the average velocity of the ball between t equals 0 and t equals 2 seconds. Right, so on average, between t equals 0 and t equals 2, how fast is this ball traveling, like this question's asking?
Mr. Martin, why did you say acceleration is divided by 2?
Well, I didn't say why it was divided by 2, but it is.
Okay, so it'll be given, it's not something we should know, right? It's not always the same thing.
Oh, this is always acceleration over 2, yes, but that's a physics principle. It's not. Actually, it's a calculus principle. I can't explain it until we get to integration. But we'll get there. So assume this is given to you. Right? Assume I give you this, which comes from this formula. If you know it, great. If you don't, ignore it and just assume I give you this. Okay? Then the question is, what's the average velocity of the ball? How do you find average velocity? Do you remember?
The slope formula.
Yeah, average velocity. So velocity in general, it's speed, right? Except it has a sign. And the way speed works is it's like miles per hour. It's distance over time, or position over time. So when you do average velocity, you take the position, the distance that you traveled, which you get by taking your final position minus your initial position. This is also called change in position, delta S. And you divide by the time that has elapsed, 2 minus 0, which is called change in time. So this is kind of, average velocity is a slope, and this is sort of the shorthand notation for the formula. You do change in distance or change in position over change in time. In this particular case, that amounts to finding the position at 2 seconds, subtracting the position at 0 seconds over 2 minus 0. So how do I actually calculate S of 2?
Plug it into
You gotta plug it in. Right? S of 2 means to plug 2 into this formula. So somewhere on your scratch board, you have to calculate S of 2, which equals negative 16 times 2 squared minus 22 times 2 plus 220. Which this is negative 64 minus 44 plus 220.
Minus 220.
What? Oh, minus, yeah, on this part, right? So this would be negative 108 plus 220. The 220 is going to cancel, but let's just ignore that. If you actually calculated it out, this would be 112. So you put 112 in here. And that's what you get when you do S of 2. Then you would do S of 0. That one's quick, right? You just plug in 0 everywhere you see T. So this will be 220. So you put minus 220 over 2, right? 2 minus 8 is 2. So this ends up being negative 108 over 2, negative 54. Because it's a velocity or a rate of change, I would label this feet per second. It's telling you how feet are changing every second. So that's how average velocity works. Remember that? Vaguely? Keep this up here. What changes if I want instantaneous velocity? Yeah, so finding instantaneous velocity at, let's do t equals 2. So instantaneous translates to derivative. So in order to find the instantaneous velocity, I'm going to have to first take the derivative of this function. So I'm going to take s prime of t, which is equal to, well, we got to do the work here. The 2 is going to come down, multiply by the negative 16, and then subtract 1 from the power. Negative 32t.
Minus 42.
And then the derivative of t is just 1, so all you'll have left here is minus 22. Because when you derive t, it goes to 1. And then when you derive 220, it goes to 0. So then we actually want the instantaneous velocity at 2. So we would do s prime of 2. So plug in 2, negative 64, minus 22. Yeah, so negative 8. So at t equals 2 seconds, you're going negative 86%. There's one other quantity that we usually care about in these kind of problems, which is the acceleration of the object, how fast the velocity is changing. Okay, so acceleration measures how fast your speed is changing. So I could ask, let's just do instantaneous. Find the instantaneous acceleration. At t equals 2. So the idea is that acceleration is the derivative of velocity. So acceleration is to velocity as velocity is to position. Yeah, so to actually find the acceleration, you take this velocity, this instantaneous velocity function, and take the derivative. The derivative of the derivative, that's correct. So a of t will equal negative 32. The acceleration of this object is negative 32 feet per second squared, always, because the only thing that's making it go any faster is gravity. Gravity is a constant acceleration. So kind of the way it works, if you have a position function and you want to get velocity, you do the derivative. If you have a velocity function and you want to get acceleration, you do the derivative again.
So, understand the acceleration is second squared, but how come when you do the derivative it squares the unit on that?
Because it's the, so when you actually do velocity, you're doing this limit. Limit is delta t goes to 0 of s of t plus delta t minus s of t over delta t, seconds on the bottom. Right, this is the derivative formula.
And the second derivative.
The second derivative means you're going to take this guy, which already has seconds on the bottom, and do it again. So you're getting, technically you're getting feet per second per second. Because you're getting velocity, but then you're dividing it by another delta t. So that just simplifies the feet per second squared.
makes sense.